Today, we're going to dive into the world of parallel programming and talk about a really cool tool that makes it way more accessible than you might think. It's called OpenMP. Let's jump in. So let's start with a simple fact about modern computers. Whether it's your laptop, your desktop, whatever, the processor inside has more than one core, just sitting there, ready to get to work. And that is the million-dollar question, isn't it? See, by default, most of the code we write runs on just a single core. It just goes through one instruction after another, totally ignoring all that other processing power you have. It's like having a whole team of people ready to help, but you're only giving work to one of them. So you might be wondering, why doesn't everybody just use all the cores all the time? Well, historically, it's been a real headache. Trying to get different parts of a program to cooperate without tripping over each other has been seriously difficult for developers. I mean, just look at this. This is a classic example of the hard way. It's called p-threads. You're having to manually create threads, manage their memory, pass pointers around. It's incredibly complex, super easy to make a mistake, and honestly, it's just tedious. But what if I told you there's a better way? A way to get your program running in parallel without having to rewrite the whole thing from scratch? Well, that is exactly where OpenMP steps in. Okay, now this is the money shot right here. On the left, you've got that complicated p-threads code. And on the right, that's the OpenMP version. All you did was add one single line, one special instruction to your original code. That's it. This comparison just perfectly shows you how simple and powerful OpenMP can be. So, what is it technically? Well, OpenMP is basically a standard set of instructions for multi-threaded programming. It's not some brand new language you have to learn. It's just a set of commands you can give to your existing C, C++, or Fortran compiler. And what's really cool is how you actually use it. About 80% of the time, you're just using these simple little compiler instructions, these directives we just saw. You're not getting bogged down learning some massive complicated library. You're just learning a handful of really key, powerful commands. All right, so you're probably thinking, this sounds great, but how do I actually get started? Let's break down how you can take a piece of your own code and get it running in parallel, like right now. The magic word you need to know is pragma. Now, a pragma is just a standard way in languages like C and C++ to give special instructions to the compiler. Think of it like a little note to the compiler. And in our case, we use #pragmaOMP to say, hey, this next instruction is for OpenMP. And really, it is this straightforward. Step 1, you find a block of code you want to speed up, and right before it, you add that #OMP parallel line. Step 2, when you go to compile your code, you just add one little flag. -OpenMP. And step 3, you just run it. That's it. The compiler takes care of all the hard stuff, creating the threads, managing them, all of it. Okay, so we've unleashed our team of threads. Awesome. But now we've got a new challenge. How do they share data? Because if you have a bunch of threads all trying to write to the same variable at the same time, you're going to have a bad time. Luckily, OpenMP gives us some simple tools to manage this. The default setting for variables is shared. This means every thread can see and change the very same variable in memory. Now, this can be useful, but you gotta be careful. If two threads try to update that variable at the exact same instant, they can interfere with each other. That's called a race condition, and it leads to all sorts of wrong and unpredictable results. So to avoid that chaos, you can declare a variable as private. When you do this, every thread gets its own personal copy. It can do whatever it wants with its own copy, and it won't affect what any of the other threads are doing. But that leads to another question. What if each thread is calculating a partial result? Like, they're all adding up a small part of a huge list of numbers. How do you safely combine all those partial results into one big final answer at the end? This is where the reduction clause comes in, and let me tell you, this thing is slick. You just tell OpenMP you want to do a reduction with an operator, like addition. It gives each thread its own private copy to work on. Then, at the very end, OpenMP safely and automatically combines all those private results back into your original variable. It's pretty much the best of both worlds. Okay, so we've looked at some of the details. Now let's kind of zoom out and look at the big picture of what's happening when you run an OpenMP program. The whole thing follows a really elegant pattern called the fork-join model. Just think of it like this. Your program starts out as a single main thread. We'll call it the master thread.
It's just chugging along, executing code one line at a time. But then it hits one of our pragma parallel lines. And at that moment, it forks, creating a whole team of worker threads. Once they're all done with that parallel block of code, they join back together, and only the master thread is left to continue on.
So the whole life cycle is this. Starts as one, forks into many to do the heavy work in parallel, and then joins back to one. This fork-join cycle can happen over and over again throughout your program. It lets you switch back and forth between running in series and running in parallel, wherever it makes the most sense.
So, what's the big takeaway from all this? I think the best way to really understand the philosophy of OpenMP is with a little analogy.
For way too long, a lot of us have been writing code for just a single musician, one CPU core. OpenMP, well, it hands you the conductor's baton. Suddenly, you can step back from trying to micromanage every little thing. Instead, you get to direct the entire orchestra of cores inside your CPU, getting them to work together to create something way faster and far more powerful. It's a total game changer in how you can think about writing code.